Hello everybody, and today we're going to be talking about the Riemann hypothesis. So actually in the last video we talked about how the series 1 over 1 plus 1 over 2 plus 1 over 3 etc. Diverges, and you can show this easily by bounding each by bounding first 1 and then 2 and then 4 and then 8 and then 16 terms all below by a half, and then it diverges. And we saw that 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, etc. This thing doesn't diverge, this thing converges, and it equals to pi squared over 6, as Euler showed. It was actually one of the first results of Euler, which made him pretty famous at the time. Also a lot of debate about whether his solution was valid, but later he corrected it by giving another proof. But that's another story. Well, and you can think about all these series as these two series as being inside of a whole family of series. Namely the one where we take any power s in the as the power of these things. So this is well, at first you might try s to be an integer and then a real number. But it turns out we can define this thing for all complex numbers s, except for when s equals 1, but we'll talk about that later. So this series is denoted by zeta of s. This is the Riemann zeta function. And we can write it also as the sum from n equals 1 to infinity of 1 over n to the power of s. And well, this function turns out to be really interesting. So first of all, we can write it in another way. So that's also done by Euler. Well, so here we've got all of these terms, but if we would multiply zeta of s by 1 over 2 to the s times zeta of s, then we see that we get and this 2 and this 1 multiplied, and we get 1 over 2 to the s plus 1 over 4 to the s plus 1 over 6 to the s, etc. So if we would take this first sum and subtract this second, we see that we get 1 minus 1 over 2 to the s times zeta of s is going to be equal to well, we've got all the even terms and we subtract them, so we only leave the odd ones. So 1 over 3 to the s plus 1 over 5 to the s, etc. And we can do the same with 3, and we multiply zeta of s by 1 over 3 to the s. And well, we have to do that with this thing we've created down here, and you would see that we get all the things that are divisible by 3, and the numerators are divisible by 3. We see that we can get those terms, and by subtracting that from this, we can kill that off. And when you would do that, you kind of see that it's going to turn out to 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s, etc. for all prime numbers, times this zeta of s, and that's really ugly zeta, but you have to do it. It is what it is. And here we can kill off all of these terms, and we left with only 1 over 1 to the s, which equals 1. And then by dividing all of these things to the other side, we see that zeta, well, that's even uglier, zeta of s equals the product over all p prime of 1 over 1 minus p to the negative s. Well, the argument we gave here is not really rigorous. Why this should work, why all of this converges, all of these terms, but you can quite easily give an argument, a rigorous argument that will show exactly that this is true. So Euler did this, and this is a famous equivalent definition of the zeta function, and it's the first time we see the connection between the zeta function and the prime numbers, because the connection turns out to be quite strong. Well, this zeta function, when you try and compute these values, we saw earlier that zeta of 2 is pi squared over 6, and it's up here. For 1 it seems to diverge. You can check that at this moment our zeta function is only defined for the real part of s being greater than 1. So that's why we can solve the 1 over 1 plus 1 over 2 plus 1 over 3, etc. And also for negative numbers and things with imaginary parts, the real part of s is less than or equal to 1. For those we can't compute this. But there's a nice observation how we can make this, how we can compute these. But let's recall a famous fact from complex analysis. If you have a function which is analytic, we can make an analytic continuation, and which means that if you know it for some part of the complex plane, what its outputs look like, you can there's only one unique way to continue it on the rest of the complex plane. If you want the function to have some certain properties, what we call being analytic. For this we want to turn all the signs for the even ones, we want to turn them to negatives, and we can do this by taking our zeta of s and multiplying it by 2 times 2 over s. And well, then we get exactly twice the sum of the even ones, 1 over 4 to the s, etc. And so if we subtract this from our from zeta, we see that we'll get this thing alternating, 1 over 1 to the s minus 1 over 2 to the s, and we subtracted it twice, so its sign changes. And so plus 1 over 3 to the s minus 1 over 4 to the s, etc. This is alternating. We could give an explicit formula for each term from n equals 1 to infinity of -1 to the n plus 1 all over n to the s. This is called the eta function, denoted by an eta of s, and this thing is defined and by this relation we're having that now. If we know the eta function, we can calculate the zeta function, and the eta function is defined for the real part of s being just for the real part of S being greater than 0, and we only needed it to be less than or equal to 1 because we already know the zeta function on this interval less than or equal to 1. But you can check this is analytic, etc. So we've extended this zeta function in this unique way, which we know exists, to make it work for all imaginary numbers with real part being bigger than 0. So that's quite nice, but we can do better. And that way we'll use another functional equation for the zeta function, and this thing we're actually not going to prove. It looks quite scary, and derivation is quite long, so we won't do it right here. But you can prove that zeta of S equals 2 to the S times pi to the power of S minus 1. And we got the sine of pi times S all over 2. And we got the gamma function of 1 minus S. And its final, we got a zeta of 1 minus S. So that's quite a long formula. And this formula works for the real part of S being in between 1 and 0. But we can pretend that it works on the whole complex plane. And it turns out when you do that, because you can reflect each, you can reflect all positive numbers to greater than half, than to I think it's less than half. By this term zeta 1 minus S, so we already knew everything above half, so we can reflect it with this formula. And it turns out when you do that, you get the whole analytic continuation you wanted of the zeta function. And when we one thing people are quite interested in are the zeros of this zeta function. So remember that we had zeta of S being equal to the product over P prime of 1 over 1 minus P to the negative S. And as you can see, this worked for the real part of S being bigger than 1. And in this product, none of the terms will ever be 0, because then P to the negative S need to be 1. No, that won't be. Then this term would be infinite. So no, this thing is never actually equal to 0. So that's a quick scene. So by this reflection formula, we see that this thing, when we're going for the real part of S being less than 0, this thing will never be 0, this thing's never 0, these things are never 0. So the only thing which can be 0 is this thing, and it turns out it quite often is. So when is this equal to 0? That's when S is n negative 2 times n, for n a natural number. So a sign of an integer times pi is equal to 0. So we see that this thing is 0 then, and sign is never nowhere else 0. So we found all the zeros for the zeta function for the real part of S being greater than 1, or for the real part of S being less than 0. So if we draw the complex plane, we know everything right here. Its zeros, those lie down here, and it's nowhere else 0. And for this is the line x equals 1. We know all of its zeros down here, which is just nothing. So the question is, what happens in this strip? Well, one can find that when one searches for some zeros, and you can calculate them with a computer, and there's some zero here, some zero here, some here, some down here, and it turns out all these zeros you find lie on this line down here, which has real part a half. So then you might ask, are these all the zeros of this? These are called the trivial ones. We know how these behave. We don't know how these behave. And are there some outside of this critical line? Is there maybe some one here or some other place, some really far above? And that's the Riemann hypothesis. So we don't know. And there is a deep connection between the zeta function and the distribution of primes. And it has to do that the real parts of the zeros and of the zeta function give some bound on the variation in the distribution of primes. And notice, because we have this reflection formula, that every zero on this side will also produce one on this side. And when you take 1 minus s, you look in this formula. And so the nicest these can be, these zeros, when they have all real parts equal to half, because that would mean the primes behave is the best, the most controlled way of behaving. That would be the case for the primes, if that were true. But we don't know. And that's the question of the Riemann hypothesis. There have been many times people claim to be proven it. It's actually a few weeks ago, some people on the internet, some news media got really excited about a certain proof that was quite old and it's already been rejected as being a true solution. It's actually one of the Millennium Prize problems, so you get $1 million from the Claymet Institute if you solve this problem. So if you want to try and solve this problem, maybe you'll succeed and you get you get $1 million. That would be nice. But that's all about the Riemann zeta function for now, and I wish you guys all